So the next talk, it's differential cryptanalysis of the reduced pointer authentication code function using ARM's feedback karma feature. And the talk is given by Shivam Ghosh. Thanks, Shivam.
Thanks for the introduction. So I'll discuss about differential cryptanalysis on PAC Karma 3 feature. This is my joint work with Roberto and Or. So here is the outline of our discussion. So I will briefly introduce how PAC Karma 3 feature work, then a differential cryptanalysis, so overview of a differential cryptanalysis on that function, and then we'll discuss some how to actually compute data time and success probability for the attacks, and then some experimental verification, and I'll conclude with the results. So the PAC feature was introduced in ARM version 8 architecture in 2016. This is basically computing a small tag based on the return address of a function and some context information. And then during function entry of a program, you insert the tag with the pointers, and upon exit, you will check the tag. Verify the tag. So VSI is like in this picture, we can see that the address space up to VSI and the upper bits are the tag. So this is an important feature for protecting against this attack, which targets tag manipulation, and it can be considered as a first line of defense for billions of devices which use this architecture to system software and complex programs such as browsers. The first PAC feature was introduced with Karma 5, which is a 12-round version of the Karma. However, for later recent resource constant device and for efficiency purpose, Karma 3-round Karma, it is 8-round Karma was introduced in PAC Karma 3 feature, and this is our main discussion. So Karma version 1, also Karma version 2 is a tweakable block cipher, and it is a reflection cipher. The encryption and decryption circuit are similar, provided you actually set the encryption and decryption keys properly. And inside PAC feature, the pointer is used as a clamped plain text input. So we call it clamped because the upper bits, so it's Karma is a 64-bit cipher, the state is 64-bit. So the upper bit is set to 0. The context, which is a public information used as a tweak, and the tag is the chopped cipher text. The attacker can only observe 64 minus VSI bits. So it is a high level overview of Karma. So there are two kinds of rounds. One is full round is R, and the first and last round basically is a single S box layer. The full round R is composed of 3 operations: the S box layer, mix column, and then a shuffle layer. And on this side, you can see the representation of Karma state. It can be represented as a 4x4 state of cells, 4-bit cells. Now, I'll give an overview of differential cryptanalysis on this PAC function. So here is the a high-level overview of our attack. We divide the total cipher in 3 parts. One is our mid rounds, the middle rounds for which we aim to find a differential distinguisher. Then we will use it for key recovery from the front, RIN rounds. And one thing to mention that no difference and no control over the clamped bits. Adversary has no control there. And the output is chopped, so adversary can observe only U bits. There is one thing called DIN. So DIN is the number of active bits at the plain text, and DOut is the number of active bits at the output. As adversary can observe only U bits, we are interested on those active bits which actually intersect with the U bit. So it's called D hat out. And we denote the different probability of the differential distinguisher with 2 to the power minus q. So to clarify the notation, here is an example of 52-bit address space. So this is a distinguisher. The distinguisher start from first round of the S-box operation, which is here, and end at the before the last round of S-box operation. And this distinguisher basically, if we extend on the both direction, it activate basically 10 cells. So DIN is 10 into 4, it is 40. And adversary can observe only 12 bits, and within that 12 bits only one active cells are there. There are many active cells at the output, but we are interested only one because we can observe only 12 bits. And our goal is to recover the master key, which is 128-bit key, denoted as W concatenate K. And the first round key is basically K.W, and second round key is K. So if we can just recover these two round keys, we can recover the master key. To make things simple, instead of recovering the second round key, we actually go one step forward and we recover an equivalent key, which is the linear layer application on K. And here is our goal. So our target is to recover this master key with 2 to the power 30 chosen plaintext weak pairs. And time complexity, if we manage to do with less than 2 to the power 64, we call it a break. And if it is less than 2 to the power 80, we call it a warning. So this is a basic overview of differential attack. I will not go into detail. So we'll use structures for collecting data, which is a common trick. And then for pair sieving, we take the collected data and throw into the cipher, and we collect all those plain text, ciphertext, and tweak pairs that satisfy the output difference. And then we'll go for guess and filter step, where we, for each sieved pairs that we collected in the previous step, we guess a key and check some of the condition. If the condition satisfy, we increase the counter corresponding to the key. To implement the counter, we use a dictionary, and we use it using FEL trees. And FEL trees is performing actually better than maintaining a full table and other data structure in our case. So now I will give a complete attack on 56-bit address space. We try to attack from 32 to 56-bit address space. This is just one of the example. So at first, for each of the attack, we use multiple characteristics to recover as much as keys possible, and then we go for brute force. So this is the first characteristics we use. So you can see that at the starting, there are 4 active cells, which is 2, 3, 9, and 12. And so there are 16 bits we can recover. So for each sieved pair, we choose the first round key and go forward and check the condition after the S-box layer. And then we can go one more step, which we call peeling. So we can recover 8 more key bits, because after the second S-box operation, there are 2 active cells, which are 9 and F, and we can use those. But the problem is to do that, we have to actually encrypt one full column. And so we need to guess few more key bits. For example, here we need to guess sixth cell of K.W. And which to encrypt which column, which key cell we need to guess, it depends on the shuffle layer, which is tau, and it is shown here. Similarly, we can use this characteristics to recover a few more key bits, and this to recover few more. So the point is that we use multiple characteristics to recover as much as keys possible. Here is the attack is summarized, which key cells recovered by which characteristics is shown here, and B denotes the brute force. So time complexity of this attack is 2 to the power 60, and the data complexity is 2 to the power 25. And most of the cases, the time complexity is dominated by the brute force step. Okay, so Now I'll discuss a bit about data complexity, time complexity, and how we compute this and the success probability. So this is an important step in our attack because of the chopped output, the noise level is really high in our distinguisher. So perfectly estimating this complexity is important. So, for example, we can see these characteristics I have discussed in previously. So, the output adversary can observe 8 bits, and both of them are 0. The difference is 0. So, here we want to recover 16 key bits. The probability of the distinguisher is 2 to the power minus 10, but a random pair satisfies the output difference with 2 to the power minus 8. So, this is a huge noise. So we ask this question that how many pairs we need that satisfy the input difference to recover the key. So we take two random variables R and W corresponding to the counters of right key and wrong key. And these two random variables satisfy the following distribution. Now, what we want is that we want to distinguish these two distribution because we are taking the key which have the most counters. So here is an just in visualization. So basically, the picture on the left, that is our target. We want to distinguish these two distribution for the wrong key and right key, and ER denotes the expectation of the right key counter. So we want that as less as possible the wrong key pass this threshold. And this can be done using this equation. Basically, sigma denotes the standard deviation. So we want the difference should be some standard deviation unit so that we can actually distinguish them. And for the success probability, actually, we want that for any integer a, the wrong key, the counter corresponding to the wrong key should be less than or equal to this expectation of right key. So using this formula, we can actually compute how much data we need. So gamma is equal to 8 gives a high enough success rate for these characteristics, and we can estimate the data and time complexity from this equation. Now, all these things are true when some underlying assumption is true, which is wrong key randomization hypothesis. But we know that for lightweight block ciphers, there are previous research which show that this sometimes fails, this hypothesis. So we did experimental verification. Okay, so let me explain this table. This looks bad, but the idea is that we want to, so given a characteristics, we want to verify how many actually good data we have. So HI bar denotes the number of pairs that satisfy the output difference at the ith experiment. But for each experiment, we also have a high noise level. So once we subtract this noise from the actual collected data, number of collected data, then we get the estimate, which is HI bar minus eta, and that is marked as a gray. And from that data, we can also estimate the probability. So on the left side, we can see that the theoretically estimated probability is Q, and Q bar is the experimental verified, which is quite close. Also, we call an experiment a success when it has enough signal to key recovery. And we consider this threshold that if the value is at least half of the standard deviation unit, gamma standard deviation unit, then we call this experiment as successful. But we can see that there are two characteristics, 4 and 5, for which success rate is 25% and 50% respectively. So what is wrong here? So we investigated a bit and we found conditional characteristics here. So experimentally we checked that this two key addition between second and third round S-box operation, it is actually influencing the characteristics. So it need to satisfy some specific equations, then only these characteristics will be valid. So here is a most zoom in view of the thing. So basically we can see that there are two S-box transition. One is 4 to 1 and one is 4 to 2. And for this S-box transition, there is a specific set of values which we need to take. And so basically the tweaky should be belongs to a specific set. And this set has a some structure. And if we do some computation, we can see that there are two equations that tweaky need to satisfy. Then only this characteristic is valid. So two equations, probability is 1/4. That actually explain 25% success rate. Similarly, for the other characteristics, we get one equation. I'm not discussing it here. Okay, now let's discuss the results. So here is the results we obtain. So let's start with the good thing, which is 32-bit address space. For both A profile and M profile, it seems giving good security in terms of data complexity. For 30 and 36 and 40-bit architecture, for 40-bit address space, data complexity, it's provide adequate security. But for 44 to 56, according to our target, actually it does not meet the expected security level. Okay, so let's try to conclude. So we propose practical attacks on Karma 3 that used in PAC Karma 3 feature. So if we just forget about this clamping and chopping and Karma 3, PAC Karma 3, then also our attack outperforms previous attack on Karma 3. And this version 44 to 56 do not meet the expected security level. And it is worth to mention that 44, 48, and 52 are the addresses that used in most commodity devices. Another conclusion is that finding good key recovery characteristics for clamped and chopped cipher is actually challenging. So last Saturday on workshop on automatic tools, we discussed one important thing, that finding distinguisher and key recovery are not two independent thing. So we also observed this in our work, and based on that, we did not try to find a good distinguisher only. We try to find a distinguisher that is good for key recovery. And based on that, we choose our cost function. We gave some example and heuristics in our paper. And we also observed strong clustering effects. One important future direction of our work can be how to actually directly translate our work to PAC Karma 3, because this cannot be translated directly, because collecting all those data we required for the attack is hard. And second thing is that can we extend this framework for Karma version 2? So all of our code and modeling and verification code are available publicly. And thank you.
Thank you very much. Are there any questions in the room? I see one there. There's another one here. Maybe Roberto, you can start. Okay, you can ask the question if you want, because
Okay. So just one thing, I have to defend my previous employer. Of course, the function itself is still a very good deterrent.
Yeah.
And your results, well, our results show that actually the structure of Karma is quite resilient, even to quite some massive run reduction. But of course, I mean, it does go way below what would be claimed for Karma 5.
Yes.
That's the point, because the ARM decided to reduce from 5 to 3. And so it is reasonable to put the feature to the same scrutiny.
Yep.
Yeah. That's the point here.
thanks. There was a question there. Maybe in the meanwhile, sorry, Shivam, in the results, there was only one line with multiple differentials. Is there an explanation?
Yes. So for 42-bit address space, we have two attacks. One is actually with normal differential attack, but later we found related to multiple differential, which is giving better results. So basically, we use 44 characteristics, which look same from the starting and end, but they have different inputs, and that actually improving the attack.
Okay.
So yeah.
Thank you.
So sorry, I didn't mention it.
Okay, so thank you for the talk. I have two questions. One is if someone carefully chosen the output station, do you think it can have better resistance to this kind of attack? This is first one. And the second one is did ARM planning to do any modification for their schedule according to your attack?
For the second question, you can talk to Roberto, who knows this law things better than me. I don't know how they are doing, but the actual problem of our attack to directly translate to practical pack feature is that collecting data, because we need chosen plaintext attack, and collecting those chosen plaintext from actual implementation of pack function may be hard. This is a future direction we can look at, because this has a nice practical implication as well. Yeah.
Thank
Okay,
you very
thank you.
much.
Thank you.
Thanks. So let's thank Shivam again. Thanks a lot.